Good afternoon.
Good afternoon, sir.
Uh, okay, let us wait for 1 2 minutes and see if some other people will join, and then we'll start today's session. Good afternoon, everyone. Is the screen visible and am I audible? Can you please confirm that?
Yes, sir. Screen is visible and you are audible.
Thank you so much. Good afternoon, everyone. I'm Adnan Farooq Khan, and today is our final session for this course, Design of Power Electronic Converters, which is being taught by Professor Shabli Nath from IIT Guwahati. As I told you, like today will be today is the week 8th of this course, and today will be the final problem solving session for this course. And like every other problem solving, firstly, I'll go through whatever has been taught during this week, and then subsequently we will move towards problem solving, and that should help you in solve your assignments and so on and so forth. And if you have any like questions, and you can ask, you can uh, text in the messages, or you can unmute yourself and ask the questions. So coming to the today's problem solving session. So firstly, during this week's this was mainly about designing the power electronic converters in PCBs, and about different aspects or sections of the power converters, where we see what are the different aspects of the power electronic converters, and subsequently what was told, what was being taught was about like capacitors and types of the capacitors, how to choose them, and then subsequently about the PCB designing. If you want to design a particular converter, how to design the PCB for that converter, how to route, and how to choose the components, and so on and so forth. And also what was being talked about, like the different types of grounds that we have in our circuitry, and more what was taught is what are the different aspects that we should take into the consideration, or should take care of while designing the PCB or routing, and so on and so forth. We shall go briefly through all those things, and then subsequently we will move towards the problem solving. So coming to the different sections of the power electronic converters, you can divide overall the circuitry into the different sections, where we'll be having the power electronics, and in that thing, what will mostly come are like the power components or power circuitry. And then there's another section of the gate drivers, which we have seen in the detail, the gate drivers that are used to drive our switches, MOSFETs, be it MOSFETs, IGBTs, um, and the other section of the converter are the controllers, where which provided us with the switching to the which take into the control action, and then provide the appropriate switchings for our devices, and so on and so forth. And the other part of the overall converter is the sensing circuitry, where if we want to sense different things like the voltage and currents, and this thing comes into the picture, and we need certain certain sensing circuitry for that purpose as well. Then there will be some interfacing circuitry if we want to change the voltage level, or if we want to provide some buffer, some interfacing circuitry between the sensing, or power circuitry, or the high power or low power circuitry. Then this interfacing circuits come into the picture. And there are other aspects are like power supplies, like if we need different levels of power supply for our gate drivers, for sensing purposes, for interfacing circuits, or controllers, and for that we require different power supplies. And for that, we'll be having some auxiliary power supply in our converter, and we'll look into that aspect as well. The other major aspect of the power electronic converters are like the cooling, we saw in our converters, and there will be some losses in our converters, and because of those losses, there will be some temperature rise, and we want to dissipate that heat, so that our uh, converters are not affected or not damaged, and so for that purpose, like we need some cooling circuitry. We can have a simple cooling, or we can have a air cooled or water cooled system, depending upon the application and the type of the converter. And the other thing will be is the enclosure. And you may see a number of converters that will be enclosed in some enclosure. And or it will depend upon the application and where we want to where we want to have our circuitry. And depending upon that, we can have the enclosure. In some cases, like there will be a general enclosure be where we can have the overall some external enclosure where we can have the n number of converters inside, or we can have a separate enclosure for each of the converters in some cases. So moving to this, here, like we had taken an example of a three-phase motor drive motor drive that has been developed by Wolfspeed. Is like of a 7.5 kilowatt. And if you and this is the part number that has been provided for this converter. And if you like search for this part number, and you can get the application notes and their design files and everything for this converter. And subsequently we'll be seeing into the different aspects of this converter, gate drivers, controllers, sensing. You can see those documents in detail, how they have developed, how they have developed this motor drive, three-phase motor drive. And you can just search this part number or go to their site, and or you can get the detailed files for this converter. And subsequently we'll be seeing what is inside this converter. So coming to the first section of the power electronics, for this three-phase motor drive, like you can see, we have three-phase AC supply. Then whatever is in this black is shown in this black forms the power circuitry of this converter. And in that, what we will be having an AC source, and which will be connected to the three-phase rectifier. This is an uncontrolled one. As you can see, it's a mirror of diode, and in between the source and this we can have some EMI filter and protection circuitry. And then there will be a DC bus. And after that, DC bus, we have then there will be on DC. This forms the AC DC part. And then after this DC, we have a two-level three-phase inverter, and which drives this motor. And you can see here the inverter is driven by is formed of this MOSFETs, and each leg of this inverter forms of this MOSFETs. Overall we have total of 6 MOSFETs. Then subsequently it is driving a three-phase motor. And below here, in this we can also see there are sensing circuitry here, voltage sensors which sense the voltages. We will be having a controller which will be providing the gate signals to these MOSFETs. And we can have the sensing circuit, or there is some encoder which senses the speed of this motor. Some current sensors, we'll be seeing how this current sensors are implemented, a brief idea about that. Voltage sensors, some phase measurement sensors. We can have all that circuitry, but that will come into the sensing portion. And whatever is in this shown in this black. Black is the power circuitry, where we'll have a three-phase rectifier. And then we have a three-phase inverter. First it forms the AC to DC part, then there's a DC to AC which drives the three-phase motor. So here saw about the which components form about the power circuitry of our converter. Moving after that, in order to drive, we saw sorry for that, I shall move this here. So here now moving to the second part of this converter, we have the gate drivers. We saw towards the left is the uncontrolled AC/DC, which forms out the DC bus. Then we have the controlled like three-phase inverter, and we require the gate pulses for this in order to operate these switches, and in order to drive the three-phase mode and to generate a proper voltage for in order to drive this motor. What we'll be having, as we had discussed earlier, like in an edge bridge, like we'll be having a high side gate driver in order to drive the high side switch, and the low side gate driver in order to like drive this uh, low side devices. And what we saw there is like this low side devices usually have the common like this source potential uh, does not fluctuate. It is like at the constant potential, and you can see here the sources of these bottom devices are at the constant potential of minus VDC. But what happens is like the source potential of this high side switches, they usually fluctuate between 0 to VDC, and for that like we require like we had seen in the gate, if you can recall, like 2-3 sessions back when we had seen in detail the gate drivers for in order to drive the devices. So for these high side switches we require the isolated supplies for this floating supply at the source of these top side devices. So you can see here low for the low side what is given for this application node. They have only one this isolated supply, which supplies gives the voltage of like to drive this gate driver voltage of plus 15 and minus 3 volt in order to drive these low side switches. And here you can see for this will be having a Murata gate supply, like which has an input of 12 volts, and at the output like they'll give a plus 15 and minus 3 volt in order to like drive these devices. We'll be having a single isolated supply for these low side switches, because like the sources of these these devices are at a common potential. And then we'll be having a gate driver ICs, and which will like give us the pulses, appropriate pulses for this in order to drive these devices. But for the high side switches, as I told you, like and we had discussed earlier, these devices will be the source of these devices will be having a floating supply, and the source of these three legs won't be at a common potential. So what is done here is like for the high side switches we'll be having the three isolated supplies, and one of which is shown here, where isolated supply, and in a similar fashion then we'll be having gate driver ICs for that, which will provide the which will provide like the pulses for this these switches. Here the gate driver for the G1 switch is shown, and subsequently we'll be having a similar set of gate driver circuitry for the other two high side switches, like G3 and G5. This was this we have to keep into the mind, like we had seen during the gate driver session as well. Like we had to take care of the floating supply, and for that one of the way to do that was to have the isolated supply by which we can give the pulses, which can like provide the proper like voltages for voltage levels for in order to give pulses to this high side switches. This was about the gate driver. Now the other thing is like the controller, like the controller like action, like the controller in a particular in a particular converter can be mainly like a digital converter or an analog converter. In the analog part like we can have some ICs like which will be formed of some op amps, and to which will be providing the appropriate voltage and currents, and which will then provide the subsequent control action and provide the pulses for our devices. And the other controller can be the digital controller, here it is shown, and which is used in this three-phase motor drive power converter that's being made by Wolfspeed, and the part number of it is given. We shall be and it will take this controller is like a digital controller, and will be sensing all the currents and voltages, and then will be giving them to this controller, and will be then taking the control action in a digital manner, and will be coding all the controllers, and so on and so forth. And this where we'll be having a digital chip which will take the control action of this converter. This was about the converter controller that is being used. About little bit about the converter, and if you want to go into the detail about the converter, you can look into this controller, and different types of controllers, like how the analog controller are implemented, and how these digital controllers are implemented, and so on and so forth. The other aspect of this converters are these sensing circuits, in our power converters, in order to control these monitor or control, or for conditioning of these converters, will be we will have to uh, see the voltages, or measure or sense voltages, currents, or different things like speed or temperature sensing of this converter. We can if whatever the parameter that we want to sense, we can have a proper sensing circuit for that, and then we'll be sensing that particular thing. And here you can see in this power converter, the voltage, we can have the voltage conditioning circuitry, for this voltage sensing, and the other thing is the current sensing, and that have been shown here, voltage sensor, and to the right is the current sensor. And there are some other sensors that are being used, but I haven't shown them here, because they will work in a similar fashion, and you can go into the detail, check the application note and the design files of this converter, and see how they are implemented, like the encoders to sense the speed of the motor. Then there will be sensors, like I told, current sensors in order to sense the current. There will be voltage sensors to sense the voltages, and there are some other sensors for the phase measurement as well. There will be some sensors to some sensor to sense this DC voltage for that. And how this is done in we will be here, how voltage sensing. There are a number of ways to sense this voltage, and one such way is like this, by using a resistor divider. Here you can see in the voltage sensor, we'll be having a resistive divider circuit, where we'll be sensing, we'll be giving the for this DC voltage sensing, we'll be having we'll be giving the whole DC, and then we'll be using some resistive divider, and across that resistor divider, across the one of the resistors, will be taking the output, which will be giving to our voltage sensor IC, which is nothing but they will be at isolated amplifiers, and which would then generate a appropriate output, and this output will be proportional to the overall DC link that will be sensing. And these the output of these voltages will be voltage, if they are not, the levels are not proper, then we'll be having some other circuitry, which would conditioning circuitry, and if the voltage levels are appropriate, then we'll be directly giving this voltage to the controllers, microcontrollers, where which would then take the control actions and provide the subsequent control signals, and so on and so forth. And this was about the voltage sensor. And here in the current sensor, we can have a different types of circuitry for the current sensing as well, like the Hall effect sensors, by using the sensing resistors and so on and so forth. Here how it is done is using through the sensing resistors, like which are very high precision resistance and of very low value, because we don't want like a very high voltage drop across these resistors. uh, and these resistors, like sensing resistors, will have a voltage drop, and that will be proportional, will give the voltage drop that will be proportional to the amount of current that will be flowing through that branch. And these resistors will be like of very high precision, because there should not be any variation in the value of these resistors, because then there will be a variation in our sensing as well. And after that, they will provide a voltage that will be proportional to the current that will be flowing in that particular branch or line. And after that, like, we'll be having some RC circuitry which will act with which is like a filter or something, then that is given to this sensing circuitry, which is, like I told you, like this is an isolated amplifiers. And then after that, it will provide the output which we usually either give to the conditioning circuitry or to the microcontroller. And why these isolated these are used, we can have non-isolated as well, but as we had seen in previous sessions as well, like these isolated there should be some isolation between this power side and the signal side. And also there should be what this isolation happening, it also, if there is some noise on the power side, and this it helps in noise not getting propagated towards our signal side, but towards the signal side also, which is happening if there is some fault on the power side. And subsequently, that thing should not damage our sensing, or or the signal side or the microcontroller for that part. So this was about the sensing circuit. And now the other circuit after that, we'll be having some interfacing circuit. Like if we got some here is one of the circuitry that is shown for the voltage conditioning. Now let us say, we got some voltage from the voltage level at the output of this voltage sensor. Now this voltage is to be given to the microcontroller. We know the range for the microcontroller is between the 0 to 3 volt. If we have and also, we know the microcontroller only takes up the positive voltage, and it doesn't have it doesn't take into the account that the negative voltage. So what we want to condition our sensed voltage. Let us say we had censored an AC voltage, it will be having some positive and the negative values, but we cannot give the negative voltage to this microcontroller. So what we want to do, we want to first give the offset to the voltage. So here, if you can see, an offset of 1.65 volt is provided, because now our 0 will correspond to this offset voltage, and a voltage above this offset voltage will correspond to the positive voltage, and the voltage below this offset voltage will correspond to the negative voltage. And after that, we give that voltage to the microcontrollers. Also, if we want to change our voltage, let us say after the this voltage sensing part, the voltage that we got was in the range of in the 5 volts or 10 volts or 12 volts or so on and so forth. But we know the voltages that we can give to the microcontroller range from 0 to 3 volts. So we want to condition this voltages and change its levels. So for that we'll be having this circuitry, op-amp circuitry, which will change its level. Also by this we can we also give the offsets and so on and so forth, so we can then give this voltage whatever we have sensed to the microcontroller and take appropriate control actions in the microcontroller and provide the subsequent pulses to our devices. In a similar fashion, we can have the interfacing or conditioning circuitry for other parameters, like be it currents, temperature, or speed sensing, and so on and so forth. So this was the other section or part of this power converters. And after that, the other major part is the power supply. So if you can see, if we have these conditioning circuits, it requires different voltage levels, let us say an offset voltage of let us say 1.65 volts, or some biasing voltage of 0 to 3.3 volts. And if we had seen some ICs for this voltage current or current sensing, which require a voltage of plus 5 volt or plus 3 volt, and so on and so forth. And if we require these voltages, we need to have either we can provide by some external DC supply these voltage in externally by some DC supplies, DC source, or we can have some auxiliary supply which will take which will have the whole DC bus will be taken, and from that whole DC bus, and we shall generate different appropriate different voltage levels that will be requiring for our low power side, be it for our sensing controllers or any other circuitry. And here you can see the auxiliary power supply is given, which is made of an flyback converter, where at the input we have a whole DC, and which is then subsequently we have this then the flyback circuitry and flyback converter, which then transforms this voltage to other voltage levels of 12 volts, 15 volts, which is required for gate drivers, sensing circuits, and some other parts of the converter. And for that purpose, this auxiliary power supply is being used. This is a vital part of the power converter, which generates the different voltage levels to drive the other parts of the converter. After that, then there is the other aspect of cooling and the enclosure, as we had seen that in their devices that are provided, there will be some losses associated, and because of those losses there will be a temperature rise in our devices. And what we want to do, we don't want that temperature to go beyond a certain point, and we want to limit that temperature rise. And for that, we'll be having some cooling arrangement. Here you can see where the cursor is pointing, we are having some heat sinks with the fans, these are forced air cooled heat sinks. And these cooling circuitry, cooling or thermal management, sorry, thermal aspect or thermal management will depend upon the application or the type of the converters. We can have the different cooling system provided. We can have the air cooled, we can have the forced air cooled, we can have the water cooled, and so on and so forth. And this is an important part of this designing this thermal management. We had a particular session 1 week for that, this thermal management only, it's in itself. And then there is an enclosure which is not shown here. Like I told you, there will be some converters which will be in their own enclosure, or there will be some converters like there will be a general like sort of an enclosure where like different paths or the different converters will be inside that converter, inside that enclosure or casing. And it all depends upon like the applications and what we want to have. Let us say like if we want to have a converter and you want to like then for this mass production and have that converter into the like the market, then you'll see you might have seen like there is a proper enclosure for that for a particular or like a circuitry or the converter or and so on. That forms the enclosure of the converter, because like this has been developed for the like testing prototype. That's why there is no enclosure in it. Like if you want to have the production unit, then we need to have the enclosure, so that like we can like handle or like transport these converters easily. So this was about the cooling and enclosure. And after that, like with this like we had seen the different sections of the converter, what are the different sections of the converter and what we have to look for and while designing these converters. The other thing like what was discussed during this week is are the capacitors and different types of capacitors. As you know, like we require the capacitors in our like converters, be it for the DC bank, or like we can have DC capacitors, AC capacitors. And usually like for if we want to have the DC at the end of the DC bus, want to regulate some DC, like we'll be requiring some capacitor for the filtering purposes. Like if we have the, we'll be requiring some capacitor. Depending upon the application and the value of the capacitor, we require, like we can have the different capacitors. And there are like the main types of the capacitors are like the electrolytic capacitors, film capacitor, or the ceramic capacitors. And if you can see here in the graph, like these capacitors like vary in the amount of the value, like they have the amount of the capacitance value they have and the voltage level up till which they can go. If you can see in the graph, like if we want to have the capacitance of very high value, then we shall be, but you can see like these capacitors are usually of aluminum electrolytic capacitor or tantalum capacitors, which are usually the electrolytic come under the type of the electrolytic capacitors. So these electrolytic capacitors will be having the high capacitance value, but the voltage level ratings of these capacitors will be low compared to the other types. You can see they can go for like millifarads to farads, but the voltage rates hardly like process like the 1 kilovolt, in the range of the hundreds of volt or to 1 kilovolt or so on and so forth. So usually like, but also these electrolytic capacitors are the polar capacitors. You cannot like they'll be having a proper positive terminal and the negative terminal, and you have to take care of while like seeing, like you have to connect the proper terminal to the proper bus. Otherwise like these capacitors would get damaged if we like if we do not properly connect these capacitors. And if you coming, then there is a film capacitors, and usually these film capacitors will be having a value lower than that of the electrolytic capacitor, but they will be rated to uh, 1 to the tens of the kilovolts. Like the voltage rating of these capacitors will be very high. And if you can see here in the graph, like this power capacitors and this film capacitors come under this range. Like we'll be having, if we want to have, if you have the capacitance of lower value but require the higher voltage level, then we'll go for these capacitors. And these capacitors are highly reliable than highly reliable than this aluminum electrolytic capacitors. And then there comes the ceramic capacitors, and like if you want these capacitors will have the values lower than that of this film capacitors, but the voltage levels will be very much higher in these ceramic capacitors. So if you can see, there are some pictures that here in the top picture portrays like this electrolytic, shows the electrolytic capacitor. You can see different electrolytic capacitors. As you can see in these capacitors, as I told you, these are the polar capacitors, and uh, you have to take precautions of like the terminals. There will be some terminals that will be marked either positive or negative, or there will be marking on the both terminals, and you have to take into that account, like connect have the proper connections in that, and you cannot connect any terminal to any of the terminals in this electrolytic capacitor. And then there comes a film capacitor. If you can see here, yeah, they are usually and both they here film capacitors, if you can see, and they are not like bipolar. They are not polar capacitors, like you can connect the any of the terminal to the positive or the negative bus. And you can see that these here shown are like a through hole. They usually are in the through hole, like they will like go through the hole, then we will solder them to the PCB. And the here to the like this picture, like over which there is the cursor, like these are the ceramic capacitors, and they can have like they can be of the SMD type or the through hole type. Usually like SMD are the surface mount devices, like they will be mounted on the surface and soldered to the surface of the PCB. And the through hole will like these leads of these capacitors will go through the holes, and then we'll be soldering them to their like at their respective places. So as we have seen, now coming to the equivalent circuit of the capacitors, like we had seen that non-ideal capacitor will have like some ASR, like resistance, like parasitic resistance, and the inductor, and which will be given by the ESR or and the ESL, and after that like we'll be having the capacitor. So usually like while designing the capacitor, like we have to take into the account like we know like this inductor and this capacitor will form a resonant like a circuit, uh, and they will resonate and will be having the resonant frequency of this, like that will be given by 1 by root ls and cr. And we know at this resonant frequency, like the impedance will be of this ESR of the resistor, and below this resonant frequency the whole circuitry will be capacitive in nature. And after this the dominant will be the capacitive, and after this resonant frequency this inductance will be the dominant. So though we have to then while designing the power electronic converter, we have to take this thing into the account, like if we know this the parasitic inductance of the converter, and we know that uh, this or the operating frequency at which we want to operate our converter, like we have to see if our converter is operating the below the resonating frequency of this capacitor, because then only this impedance of this capacitor will be the capacitive in nature. So we have to see for the data sheet and see the resonating frequency of this particular capacitor, and see frequency at which we want to operate, and choose, then we have to choose our capacitor accordingly. So this was about this. And now also, like what we have to do is, like we have to we can, like, other specification of the capacitor will include, like we have to see for the like the RMS current rating of the capacitor. Like usually the average of the current that will go through the capacitor, like will be 0, but there will be some RMS current that will go, and there will be some losses associated with it because of this ESR. And also, like, we have to see for the ratings of the ripple current that will that a particular capacitor will be able to sustain before getting damaged. Also, like we have to see for the dV by dt rating of the capacitor, and see if our capacitor will be able to withstand a particular dV by dt rating uh, of the converter. If we have any converter, then we can we know then we'll be having a switching voltage at some nodes, and we can get to know what is the dV by dt rating at that particular, and we have to see if our capacitor is able to withstand that. So, like, that will be provided in the data sheet. We can, and then we have to keep that thing into the consideration as well. Also, like the failure rate, like I told you, like there are different types of capacitors. There will be aluminum capacitor, film capacitor, or ceramic capacitor. I told you, like these aluminum capacitors are not that are less reliable compared to the film capacitors and ceramic capacitors. But we like if we in our circuitry, if we have the very high capacitance, require very high capacitance, we are like then bound to, like have the aluminum capacitor. But if we want to have a, like if at some point in the circuitry we are having lower capacitance, we should, like, go for the film capacitor or ceramic capacitors, like, because the failure rate of the reliability of those capacitors is higher compared to the aluminum capacitors. So we have to take into the account these specifications, and see for these specifications in the data sheets and so on and so forth before, like choosing a capacitor, and choosing a capacitor for our converters. So now coming to this, like now we shall be, like going through some other, like components. Like you can see, like we can see what are the different types of components that can be there. Like here you can see the two major components are, like the that we use on in our PCB are, like the through hole components and surface mount components. Here you can see the through hole components usually have the leads, and there will be a hole for a particular, and a footprint for a particular component, and then these leads of that component are, like pushed through these holes, and are soldered to this at the particular terminals. And also there will be some SMD components. Here you can see the SMD components. They are like surface mount devices. Like they are usually, they'll be having their surface mount and put on the surface, and then their terminals will be soldered to their respective terminals at on the surface itself, and there are not any holes there. And usually what the parasitics for these through hole components are higher compared to these surface mount devices. And also, if you can see like the footprint, like you can see for the footprint of these through hole devices, and if you can measure here, like for resistors, like if you can see different resistors, and they will depend if you want to choose the resistors for our power components, and it will depend upon like what is the value of the resistance that we require, and what is the tolerance that uh, we can have, like if we are for if the resistors are for using the sensing purposes, then the tolerance band should be very low, because then only it will provide the appropriate measurement. But if we require like at some other places where there can be there can be some higher tolerance, then we can use the resistance of some higher tolerance. Right. Also, the value of this like resistance will depend upon the power rating, and how much of this like power is to be dissipated in this resistance will be dissipated across the resistance, and it will depend upon that. And for that we'll be having like if we are having the like you can see here the size of this, like if we have for the low power rating, like what is the size of this resistors, and as we move higher in the power level, the size of these resistors go up. And if you can see for like if you want to have the power resistor of the 10 watt and 20 watt, like you can see for the size of the resistor itself. So here we saw like as the power level goes up in the resistance, the size of like the resistance will go up. So the other things are the like connectors, like we'll be having certain like connectors on the PCBs or so on and so forth, like which will be used like for like connecting the wires, or like having the leads. And there will be some like there the voltage rating of these connectors should also be updated, and they should be able to withstand that voltage and that current level, and which will be like helping us in like connecting the different parts of connecting the different parts of the circuitry, or like the converter. And the other equipment like that will be requiring or like the oscilloscopes. Here you can see if you want to like probe, if we want to like probe a particular voltage and see a particular voltage or the current waveform, like for that what we require is the oscilloscope. And there's a picture of the oscilloscope that is provided here. And you can these oscilloscopes usually have many channels, like there can, here you can see, and we can like probe n number of like many number of like voltage or current at the same time in this on this oscilloscope. And like you can do there are many functionalities that are being provided, like you can do the math operations, you can see the RMS peak of any waveform on this oscilloscope. And for that like you need to like see for the oscilloscope operated, and you can like see what are the functions that a particular oscilloscope provides. And but one thing that is to be kept in mind, like usually these probes of the all these channels of this oscilloscope are connected to the common, or connected to the common ground. That means that the grounds of these all these channels is same. And if we want to like probe like different voltages or currents which have different grounds, so we should not do that them using the single-ended probes, because like then what may happen, like it may short, like the two grounds may get shorted, and it may damage like the oscilloscope, or may damage the oscilloscope, like if there is a fault on this, it may get propagated to other part, or damage this. For that what we use is, usually we use it, and we use the isolated probes, like isolated probes. What will this be having here two terminals where the positive will be connected to the positive terminal, and the other terminal will be connected to the ground, and these probes will be isolated, and the other part will be connected to the terminal. And if we want to see the voltages, let us say we want to see the uh, switch voltages in the two legs of the top devices, high side switches, like the grounds of which are they don't have the same ground. And for that, like what we'll be doing, we'll be using the isolated probes for that, so that the grounds of so that as we have the different grounds, we don't want two different grounds to get shorted, so we'll be using the isolated probes for that. So we have to keep these things in consideration while probing or testing the converters, or and so. Now coming to the PCB designing steps, this had been discussed in the course towards the end, towards the final lectures. In the PCB designing, what we'll be first aiming is the schematic usually forms whatever are the different components, like you will be adding them to the schematics. You can see for this three-phase AC to three-phase motor, what we had first, the three-phase different paths, there was a rectifier which was doing the rectification, and then there was a DC link where we had some capacitors at the DC link. Then there was the inverter part, and some other other components that involve the current measurement, whatever the components that are in that you want on the PCB and are there, you have to put those in the schematic. And in the schematic itself, like here you can see we have a three-phase rectifier. You have to provide a proper footprint to the particular component, and add these component in the schematic. And in the schematic itself, you have to not route, join the components properly in a fashion how the circuitry is made. So we can have the different parts, like here you saw the rectifier, DC link, inverter part. Like in the inverter we had the switches, you have to see for the part number and assign a particular and a proper footprint to this switches and other components in itself, in the schematic itself. Then after this schematic, will be then going towards component footprint. These component footprints are assigned in the schematic itself. When you make a PCB schematic on any software, you can have a Design Spark, LTM, or KiCad. Then if we want, then what we do is we make a PCB for that, and on in the PCB itself, you can see there will be whatever the component footprints that you have will be added, will be there in on the PCB. And for a particular component, you should be having an appropriate footprint. If we have a switch, it has the three terminals. It has the three terminals, like the drain, the source, and gate. Or if we have a four leg switch where we have a Kelvin source, we want to use that the component, we have to add the proper footprint for that itself. Similar fashion, if we are having a certain IC, we have to provide the proper footprint of that IC itself. Then only so that each pin of this IC will have its own place where we can then place this IC and solder its particular component. And here also you can see for the capacitor itself, there should be the proper terminals and proper footprint of the capacitor itself. So in the nutshell, what we do, we have to provide the proper footprint, and then only when we get the printed PCB, we'll be able to, sorry, one more, we will be able to we will be able to add a particular, we will be able to add that particular component on the PCB. If the footprint is not correct, then there can be some misalignment and we won't be able to solder that component on the PCB itself. So we have to take the care of this component footprint and add the appropriate footprint for a particular this component. And the other thing is the placement and routing. After that, when these components are added in this on the PCB, then we'd have to do is we have to then properly place these components on and route these in the routing itself. Routing will mean that connecting the different terminals in on the PCB itself with the copper. In the copper layer we can have the planes, we can have the routes for a particular thing, and we'll be seeing what I mean by those here. If you can see whatever the PCB that has been made for this prototype, you can see the placements. Like here you can see if the A part, this is the input AC terminal voltage here, that is shown in the green. The B part, you can see a proper footprint of an EMI filter, some capacitors and some choke. And similar in a C, this is a diode bridge rectifier. See, this is the three-phase diode bridge rectifier. We have a single IC for that, and we should have this which had its terminal and all the three legs of the three-phase diode bridge rectifier on it itself. And in a similar fashion, there are you can see it has been named here. This material will be provided to you. You can see all these circuitry and their footprints are provided here, and we have to optimally place them. We don't have to place these devices or the components far away from here, because then what will be the size of the PCB will be large. Also this routes between the different components will be very large, and which may increase our parasitic inductances or the capacitance. This was about the routing, and what we have to keep in mind in the placement and routing is in firstly as I told you, we should keep into the in the routing. What we should be keeping the mind is to minimize this parasitics like resistance, inductance and capacitance. For that also whenever we have to we for that, what we have to do is we have to optimally place these capacitance as near as possible we can. But also what we have to keep into the consideration is the thickness while routing, is the thickness of this copper and the trace width, connecting these the different components, because these traces they carry the current, and we have to calculate the appropriate things. But there are a number of calculators are provided with the softwares itself. In the KiCad, you can see in the Altium, for a particular current rating, they will tell you what is the minimum of this width of this trace and the thickness of the trace that you require for a particular current level. And if you then increase the width or the thickness of this trace, and that will subsequently decrease the resistance of subsequently decrease the resistance to the current. As I told you, also the copper and thickness and trace width should be properly calculated in order to because for the particular current that we need to that it needs to carry, or whatever the current we want to flow through that trace, it should be able to handle that amount of current, and for that, like, we have to calculate the proper width and thickness of that current, so that the temperature, because there will be some parasitic associated with these traces, and the temperature of these should not rise beyond the limit, so that our PCB may get damaged. Also, like, between any like traces and or the terminals, or like between two paths, there should be a proper clearance, and that will be determined by the voltage level. Also, what is the this here you can see, here if we have the two conductors, and there should be some insulation barrier between them, so that there is not like a sparking or a damage of the insulation barrier between them because of the voltage level. We can provide some air gap between them, or we can have some barrier between them, so that it is able to withstand that amount of the voltage level. Like this voltage clearance, the insulation between, or the space between the two paths or connectors, or like this traces, is determined by the voltage clearance. And then we'll be having the ground plane. Usually what we do is, in the PCB design, we usually keep one plane as a ground plane, because like for any of the current, we require some path, the return path, and usually we want to like minimize that thing. And usually what we do is, we can have a ground plane for that thing. And what we do is, we have the ground plane, and the currents will take the minimum route, and can like reduce it can reduce like the parasitics. And you can go into the details, see for the PCB designs. You can see some videos, or the tutorials for the PCB design in itself. Here is just a gist, or the idea that I am giving here. After that, like, what we have to keep into the consideration is, we have to minimize these loops, because like, in like, here is the example of a boost converter that is provided here. As you can see, like, here you can see the current that is flowing through this inductor. If it has this triangular sort of a shape, and we know that it has the low di by dt, but the current that is flowing through this switch, you can see it is on for some time, and then it's off. And at the time of it's like turning on, like, it has very high di by dt. And what we want to do is, we want to minimize this loop where through which this current is flowing. Because if these traces and loops will have its parasitic inductance, if we have the very high di by dt, then because of the L, di by dt will be very high, and LDI by dt will be very high. Then there will be some voltages that will be LDI by dt will be a very high, which can like then like interfere with these devices, and like we cannot have the proper operation, and make can like our device, this circuitry won't be able to like perform like well. In a similar fashion, like we have to like for this node here, like dv by dt, this switch node voltage, this dv by dt will be very high. And if there is like a very high parasitic capacitance, then cdv by dt will be very high, which because of that, there will be some capacitive currents, like which can like uh, these capacitive currents will interact like with these other like device currents, and so on and so forth. And then like this converter can maloperate. So what we want to do is, we want to like minimize these loops, like these switching loops, like we want to minimize this, so that we can have very so that LDI by dt and CdV by dt is very less. We have to take like these things into the account. Now coming to the other part that we have to keep into the consideration is like the grounds, like in our converter there will be different grounds. We will be having the power grounds that will be at a very high power level, and there will be some low side ground, low power grounds. In the low power grounds we can have the analog grounds, like some analog circuitry where we'll be having the different voltage levels, be it of like 5 volts, 10 volts, 12 volts, or 15 volts, and so on and so forth. And there will be a separate ground. These can be connected together or they can be isolated. We have to take we have to keep in the mind the different grounds for the different parts of the circuitry, if they are connected together or if they are isolated together. And for different parts there will be a different grounds, and then there will be a digital ground. Then there is other ground, that is a digital ground, that it will be associated with the digital circuitry. That is usually like in the digital circuit we saw like it is in, or the it varies between like the 0 to 3.3 volts, and there will be some ground like this is also the low power ground. Like we in the digital circuitry itself, like we can have the different grounds, and these grounds will be connected together. Also the other ground, that will be the chassis ground. Like we can have an enclosure or a chassis of a converter, and that will be grounded itself. That is the chassis ground. And in that thing, like we can what we saw is like we can have like different types of the grounds. These grounds can be together, or like you have to take into the account of the circuitry if these grounds are connected together or these are isolated. And you have to make your schematic in such a way like to take that thing in the account, follow the proper isolation. If the grounds are isolated, we have to isolate them. Usually the power side and signal side grounds are isolated, because like we don't want if there is any fault on the power side, that should propagate to the signal side, like because the power levels of the two sides very way high, it can damage the components on the signal or the low power side. So it's about the grounds. And in the ground itself, like I told you, like if we have the different circuitry like analog circuit or digital circuit, we shouldn't have if the grounds are isolated, like what we'll have, like if the two grounds get connected, there will be some ground loop that will be formed between these two grounds. And if there is some then this loop can have its own parasitics, like which can cause some noise issues. Or also if there is some noise on one part, and that can get propagated to other part. Also, like if we have some appliances like which has the common mode current or common mode current or some noise, and if the ground of that appliance is connected to the grounds of some other components, what can happen, like this can get propagated from one part to the other, and can alter like and can affect the functioning of that particular component. So we have to like this is the way, like here I have shown like how it can like if the grounds of the two parts are connected together, which need to be isolated, like if we don't have an isolated grounds, like what can happen if we have some common mode currents in some part of the converter or the appliances, that can interact then with the other components and can alter or like the working of that component in itself. So this was about the every thing that has been discussed up till now. Like now we'll be subsequently moving towards the problem solving session. We'll be taking a break of like 5 minutes, and we'll be discussing these questions. So coming towards this problem solving session, um, this is like planes or polygons of first question that is there is like planes and polygons or different types of ground should be connected in dash node. First is like a delta in a delta fashion, that is a triangular fashion, or like B is a star fashion like a Y, uh, and then C is a ground, and then is like a power. So can anybody answer this question if anybody has the idea? Am I audible to everyone first? Can anybody like reply in the message? Am I audible? Am I audible? Okay. So can anybody answer this question? So okay, let us come to this question. So here like if we have, so if we have like different planes, like here you can see three planes, so we can connect uh, so there is like One way is like we can connect them separately, like first to second, then second to third, then third to one, forming the delta connection. Or like we can having a common plane like that will be connecting like the three in the star fashion. So first we'll be seeing, then there is a ground and power, like these are two different planes in itself. Like we can outrightly like dismiss these two options. Then now we have to see for this delta and the star connection. If you go for this delta, like there will be like different connections between plane 1 and plane 2, like plane 2 and plane 3, and then plane 1 and plane 3. So if here you can see there, for what there forms is there is a ground loop that is getting formed here. Also like the impedances like between can vary between like these planes. And then the current like sharing from this one plane to other, like uh, can take only a one path, like which has a low impedance, or so on and so forth, and which we don't want. And also what is getting formed is a ground loop, like we had seen previously, like we don't want ground loop to get formed. So the other option is like the star option, like where we'll be having a plane that will be connected here, and like we can see for the placement of this plane, so that we can have this almost the same impedance. Here you can see like no ground loop is getting formed. So the option that is being correct is like if you want to connect these planes or polygons of different types of the ground, that should be connected into the star connection. Number two, dash introduces noise from one circuit to another circuit. A star node, low power level, ground loop, or filter capacitor. Can anybody answer? I think uh, you should be able to answer this question. Can anybody answer? Okay, if nobody, like let us first see. We have seen like this star node, like there is no ground loop that is getting formed. Then that means like it cannot propagate like the noise from one circuit part to the another. Now also we had seen like if this sorry, if like the ground loop is getting formed between the like two different parts of the converter, or there is a like a common ground between an appliance or a certain like different components of the converter, then what can happen, like this can like get propagated, like if there is a noise or common mode current uh, in one part of the appliances, it can get, if the grounds are connected, it can get propagated to other components. Also if there is a like a ground loop that is getting formed between like two different parts of the circuit which has different grounds, then what can happen is like the noise from one part can get propagated to other through this ground loop. So the answer to this question is C, ground loop. Like if there is a ground loop that is getting formed in our schematic, or like while routing or in the different parts of the converter, then there is a chance like if there is a noise in the one part of the converter, that can get propagated to other. So C is the correct option to this. Number three, dash introduces high impedance between the sensor and the controller. A. Analog sensor. B. Gate driver. C. Salon-key filter. D. Buffer. Can anybody answer this question? Anybody? So if number no, am I audible to everyone or not? So if there is, if I am not audible or the screen is not visible, kindly let me know. Am I audible now? Am I audible? So coming to this, like we had seen for like the gate driver, if we have like these gate driver ICs, like they should like or the sensing part, or the sensor or the gate driver or the between the sensor or the controller. Usually like these ICs are not rated for very like high power or current levels. Like usually what we want to have, these ICs should have like a high impedance, or what we introduce like between the different paths, like uh, a buffer circuitry or a buffer IC, like which will provide very high impedance between one part and the other part, so that like we know like our controllers are rated for like some micro amperes or amount of the current, and they won't be able to handle the higher amount of the current levels or the power levels. So what we want, we provide some buffer ICs or ICs like which will be having a high impedance between the sensors and the controller, so that like high currents are not getting propagated towards the controller. Also, like if there is a high impedance, like what we do is like the noise that is from the sensing side or the power side doesn't get propagated to the controller, and which can then interact with the controlling action, and there will be some discrepancy in the control action. So the answer to this question is like D, buffer. Question number 4. Which of the following are the film capacitors? A. Tantalum, B. Propylene, polypropylene, and C is aluminum, and D is the polystyrene. Like there can be a multiple options to this question. Can anybody answer? Like if we have seen in the course, so it had been like taught in the course, like during this during teaching like of this capacitors, the different types of the capacitors, like electrolytic, film, and capacitor. And in the electrolytic capacitor itself, like can be of the aluminum or tantalum type. Film capacitors can be of polyester, polypropylene, or polystyrene usually. And say ceramic capacitors can be single layer and the multi layer. And if you look at this, and then you should be able to answer this question easily. And which of the following are the film capacitors? So usually the film capacitor are like polystyrene, polyester, polypropylene, and polystyrene. So I think option B and D are the correct for this. So for fourth, like B and the D are the correct options. Question number 5. Which type of capacitors from below can be manufactured with the highest capacitance? Can you answer this question? A. Electrolytic, B. Ceramic, C. Film, D. Ultra high voltage ceramic capacitors. So here like we had seen, if you can see, there is a graph that we had discussed earlier in itself. So we are having the different types of capacitors, like aluminum capacitors, film capacitor, or the ceramic capacitors. If we like want to high capacitance, we go for this aluminum capacitor, but these are rated for lesser voltages. Then if you want the capacitance of a lesser value but high, then we can go for like film or film capacitor, where there are power capacitors. And then if we have the lesser this capacitance value and the lesser voltage levels and voltage range to the highest voltage levels, then we can go for this ceramic capacitors. So the option to this is, if you want to have this high capacitance value, like we usually go for electrolytic capacitors. C. ESR of the capacitor varies with A. Temperature, B. Frequency, C. dV by dt rating, and D. Ripple current. So this had been like we didn't cover it in the during this what has been taught in the course, like but in the detail, but it has been discussed in the detail in the courses what has been taught during the course. So you can go through that, and if you check the data sheet of any capacitors, and you will be see there will be graphs provided there, where you can see like the ESR or of this capacitor value vary with the temperature, you can see. And in itself, in the graph towards the left, if you can see with the temperature, and there we have the two aluminum capacitor, like a wet or the solid type. And you can see in the wet type there is a like the variation is very high with the temperature compared to the solid one. Also you can solid one. Also you can see with the change in the frequency in itself, there is a variation in the capacitor range in ESR value in itself. With the increase in frequency, the ESR decreases. Like you can see, R decreases. So, and there is not much of a dependence of the ESR on dV by dt or the ripple current. So the option A and B are the correct for this. uh, 7. The ground which is connected to the enclosure of the power electronic converter is known as. So we had seen different types of grounds like analog ground power grounds, and like low power side grounds, and low power side ground, where we had analog grounds and digital grounds. Usually digital grounds are like from between the voltage level which is like 0 to 1 or 0 to like 3.3 volts, because like digital signals vary between in a 0 or 1 fashion, like they will be having a 0 or 3.3 volts, or the analog grounds will be having in terms of the voltage levels, or like 5 volt, 10 volt, 12 volts, and so on and so forth. And then there will be power grounds which will be of the very high voltage levels. That is the power ground. But if the ground is that is connected to the chassis or the enclosure, that enclosure of the power electric converter, that is known as the chassis ground. So the option D is the correct option. Question number 8. The clearance between the two nearby traces is decided by. So I think I had discussed this as well. So part A is like current carried by them, voltage difference between them, temperature difference between them, or impedance between them. Can anybody answer? So okay, we can see we had seen, like if we had different traces between them, between the if you have different traces of the conduct of different conductors, and or if we have different terminals or different paths, and what we want to have, there will be a we want to have the some clearance between them, and this clearance is determined by the voltage difference between them. So in order to that, uh, and to calculate the proper clearance, we are having the calculators provided in the software in itself, where we design the PCBs. So if we have to check for the proper clearance, because we don't want our clearance to get for a particular voltage level, the clearance should be inappropriate, because we don't want that insulation to get damaged and there will be a sparking, and that can damage our PCB. And so this clearance is usually determined by the voltage level that is being between these different traces, or different conductors or paths or uh, connectors itself. So the option for this is voltage differences between them. So this was about the questions regarding this PCB design. With this, we completed the design of the power electronic converters here in this, as you saw, uh, we touched every aspect of designing a particular power converter, be it like choosing the devices, power levels, devices, gate drivers, there's thermal management components, or like designing the inductors, capacitors, designing of the how to choose the capacitor, inductor, how to design them, how to then design the PCB, and so on and so forth. This usually covers the major portion of this designing a particular converter. And I think you should have gotten an idea, like if you want to design a particular converter, what are the different things and what are the different steps that we have to keep into the consideration. And when you'll be designing a particular converter, in the subsequent iterations, at first, you may feel this is not the proper design, this is not a good design, but subsequently when you will be designing then you'll be having a second iteration and so on and so forth. You'll be getting good at designing, and you may learn different things that you need to take into the account while designing a particular converter, designing a PCB, routing, and so on and so forth. I hope that these problem solving sessions have helped you like in understanding what has been taught, and understanding you like different questions that we had discussed, and helped you in the regard like you'll be able to like uh, solve the assignments that have been given to you. So if anybody has the questions, feel free to ask. You can like text the questions. I'm here, or you can unmute yourself and ask the questions. Any questions? If there are not any questions, then we can close today's session here. I'm here. I'm still here. If anybody has the questions, he is free to ask. Thank you everyone for joining, and